Welcome, class. Today, why tossing a coin isn't always 50-50.
Yes!
The law of large numbers explains it. In the real world, it's not always perfectly even. Exactly. Let's look at some real-world examples. Today, we'll see why a coin toss isn't always 50-50.
Huh? But it's always 50-50.
Not if the coin is biased. Watch this. The catch shows heads. See? Not perfectly fair.
Sir, isn't a coin toss always 50-50?
Not quite. It's all about probability. Watch. I'll toss this coin.
Oh, so it's only fair in the long run.
In theory, this should work, but in reality, it's different.
Sir, can you give an example?
Of course. Think about a game plan versus the actual game.
Oh, I see.
Exactly.
Sir, what do you mean by theory?
A theory is an explanation based on evidence. For example, gravity is a theory.
Oh, I get it now.
Exactly. Theoretical probability assumes ideal conditions.
Like flipping a coin?
Exactly. The probability is 50% heads.
What about real-life probability?
Great question. Real life includes physical factors like force and air. Who can give me an example?
Throwing a ball.
Excellent. Force makes it move, and air resistance slows it down. See the connection?
Well, with this round towel.
Everything you ice kid. Homo the Tynamok Sumpy Wheels. Namabelly bats I am that do.
Okay, class, let's see how this works. Watch the coin. The way you flip it changes the result. Who can tell me why that is?
Because the starting position is different.
Exactly.
Sir, what if we flip the same way every time?
That's an excellent question. Let's see what happens. If we flip both sides, we get x equals 5. Ah, exactly. Well done. Then results may become biased.
How?
Here's an example. If we sample only from this group, our results won't reflect the whole class.
Sir, what is bias?
Bias is a preference that makes us see things unfairly. For example, this equation shows how bias can skew our results. Excellent.
Now.
All right, class, bias means one side appears more often. Let's look at a coin toss example.
So if heads is 7 and tails is 3, that's bias?
Exactly. The coin is biased towards heads.
Sir, can coins really be biased?
An excellent question. A coin is fair if heads and tails are equally likely. If one side is more likely, we call it biased. Can anyone give an example? Exactly.
Sir, how does weight matter?
Great question. Weight is the force gravity exerts on an object's mass. So, heavier things fall faster? Not quite. In a vacuum, all objects fall at the same rate.
Oh, I get it.
All right, class, look at this coin.
What does it show, sir?
I'll show you. It will land on the side with 20 plus more often. See? The heavier side wins.
Wow, that's cool.
So, gravity pulls everything down. Sir, what about air resistance?
Ah, good question. Let's see.
This ball will fall with air resistance. See? It falls slower. All right, class. Air can slightly affect motion. Who can give me an example?
A leaf falling.
Exactly. And another? Yes, air resistance slows them down. Probability is how likely something is to happen.
Like flipping a coin?
Exactly. The probability is 1 out of 2. Let's write that down. Probability.
Oh, I get it.
All right, class. Probability is the chance of an event happening. For example, a coin flip has a 50% chance of landing heads.
So it's like a guess?
Exactly. A very educated guess. Who can give me another example? Sir, what is 50-50? It means half or an equal chance.
Oh, I get it.
That's a great question. Perfect randomness is tricky.
But what about a dice roll?
Even that can be influenced by tiny factors.
So it's never truly random?
Exactly. We can only get very close.
I see.
It's very hard in real life. Real life application is difficult but important.
Can you explain that?
Sure. It's about using what you learn. Practice makes it easier.
Sir, why not?
That's a great question. Let's see why.
So it has to be balanced?
Exactly. Now, who can show me?
I can, sir.
Great, come show us. Because physical conditions always vary.
Can you give an example?
Sure. For example, temperature and pressure. Exactly. Great job, everyone. Yes? A question?
Sir, what is randomness?
Excellent question. It's when we can't predict the outcome. Like flipping a coin, heads or tails, it's random. See? Unpredictable. All right, class. Unpredictable results. What does this mean?
Something you can't guess?
Exactly. Let's see it in action. I have an object. It landed heads its edge. Unpredictable. Sir, can humans flip randomly? Good question. Let's see. I'll flip this coin.
It's tails. Now you try.
Okay.
My turn. Tails.
Exactly. Each flip is random.
Yes. Sir, why?
That's a great question. It's because of this.
Oh.
Exactly. And that's why it's important. I get it now.
Thank you.
Humans repeat patterns unknowingly. Can anyone give an example?
Like checking your phone all the time?
Exactly. That's a pattern we don't always notice. What about other examples? Think about it. Yes, starting position is very important.
How does it matter, sir?
Let me show you on the board. See? The starting point changes the result.
Oh, I see now.
Exactly. Yes, it influences the outcome. You see how the arrows connect here?
How does this apply to real life?
Great question. Think of peer pressure.
Oh, I get it.
Sir, what is initial condition?
Great question. It's the starting value for a function. For example, yfx with wide anchor point.
Exactly. A perfect description.
I get it now! All right, class, let's look at starting position and force. Starting position is where an object begins, like a ball on the ground.
Teacher, what about force?
Great question. Force is the push or pull that moves it.
Sir, can science predict a coin toss?
Great question. Science can't predict a single toss, but it can predict the odds.
So it's always 50-50?
Exactly. Watch, the coin lands heads up. In some cases, yes. For example, when x equals 2, both sides equal 1/2.
But what about when x is 0?
Ah, excellent question. Division by 0 is sometimes true? Precisely.
Sir, how can it be predicted?
Good question. We use functions, like this graph. See? Input x here predicts output y here.
Oh, exactly.
Practice this. Using physics equations, we can predict this motion curve.
How does the curve change with velocity?
Great question. A higher velocity makes the curve steeper. Oh, I see now. All right, class. What do you think about these physics equations?
I think it's about motion.
Exactly. Motion and forces. Who can give an example?
A car speeding up?
Perfect example. All right, class, let's look at motion, rotation, and gravity on the board. Motion is a change in position, and rotation is spinning around an axis.
Sir, what about gravity?
Gravity pulls objects toward the Earth. It's what keeps us grounded. A rotation is when a shape turns around a central point. For example, look at this square on the board.
Oh, so it spins in place?
Exactly.
Like-
Now you try it.
Yes, perfect.
All right, class, let's see this in action. Watch the coin spin.
It's slowing down.
Exactly. The result is heads. This shows us probability in action. Gravity is a force that pulls objects down, like this apple on the board. Watch what happens when I drop this. See? Gravity pulled it down. All right, class, watch this coin. I'm going to drop it. Gravity will pull it down.
Whoa.
See? It fell straight down.
Cool.
Yes, it certainly does matter.
But how?
Well, these calculations help us measure and build things, like this rainbow. Oh, I see now!
Me too.
Great! Any other questions?
No, thank you.
Yes, a higher toss means more spins. The higher you toss it, the more time it has to spin. Does that make sense?
Yes. Sir, does spin matter?
Yes, it does. Spin is very important in physics. It creates something called angular momentum.
Like a spinning top?
Exactly. A perfect example. Okay, class, notice the board. More spin increases randomness. Watch this diagram. As the spin increases, see how chaotic it becomes? So, more spin creates more unpredictability. That's randomness.
Sir, what if spin is low?
Good question. Low spin means the object rotates slowly. We write that as L equals I times omega.
Oh, I get it now, thanks.
Great question. All right, class, let's see if you can predict the result.
I think the result will be predictable.
Exactly. Let's see how. We change one variable at a time.
Then we can predict.
Sir, is coin shape important?
Great question. A coin is a circle, but a sphere is 3D like a globe. Here's a circle, and here's a sphere.
Oh, I see now.
Excellent. Yes, design affects landing.
How, sir?
Through aerodynamics. Like paper planes?
Exactly. A great example. That's a great question. Let's see.
Yes, I saw it once.
Let's figure out the odds. It's very rare.
Like winning the lottery?
Exactly, but we can calculate it. All right, class. Rare but possible. Like finding a 4-leaf clover.
So it could happen?
Exactly. A small but real chance.
Wow, I
Great job, everyone.
Sir, does surface matter?
Great question. Surface and volume are different. Let's see.
So the surface is the outside?
Exactly. The surface area is the outside. The volume is the space inside. Yes, soft or hard surface changes a bounce. Watch this ball. On a hard surface, it bounces high. But on a soft surface, the bounce is low. So, what's the difference?
Energy loss.
Exactly.
Sir, what is experiment?
Great question. An experiment is a test to see if an idea works. We mix things, like water. That's the scientific method. All right, class, let's test our times tables. What is 3 times 4?
12.
Good. Now, 5 times 6? Excellent. One more. 7 times 8?
Sir, what happens in many tosses?
Good question. Let's look at the patterns. So 4 and 2 are the most
So
common.
it's not always half and half?
Exactly. Who can explain why? Excellent work, class. Our results approach 50 out of 50.
Wow, Sue.
How did we do it, sir?
By working together and using the color chart.
Cool, let's do more.
Sir, why many trials?
More trials give us more data for reliable results.
Oh, I see.
To reduce errors, we use this process. Who can tell me the first step?
Check the inputs?
Exactly. Check the inputs first. An error is a mistake, a wrong answer.
But sir, what if we don't know the right answer?
That is also an error. It's a deviation from accuracy. Okay, any more questions? Okay, let's look at the difference from the expected result. This diagram shows the concept. Any questions?
Is the difference always positive?
Good question. It can be positive or negative.
So it's how far off we are?
Sir, what is the law of large numbers? Good question. It means as you repeat an experiment, the results get closer to the expected outcome.
So flipping a coin will be 50-50?
Exactly. More trials give a more accurate probability.
Can you show us an example?
Sure, each flip of a coin has a 50% chance for heads. See? More flips make it more accurate. More trials give accurate probability. Who can tell me why?
Sample size.
Exactly. Let's see. With 10 trials, we might get 60% heads. But with 100 trials, it's closer to smoothing out the results. All right, class. Too random is not truly random. For example, dice rolls are random.
So it's not completely unpredictable?
Exactly. It's controlled unpredictability.
Oh, I get it.
Sir, is 10 toss enough?
Yes, 10 is a good sample size. Let's try it. I'll flip this coin. Heads! We'll keep track on the board. All right, class. These equations are still not perfect. We need to find the mistake. Any ideas?
Is it the square root part?
Good guess. Let's check it. Oh, I see it.
It's the past tense of need.
So I needed a pen yesterday?
Exactly. Good example. So needed shows it happened before. Perfect. You all get help? All right, class. Here we have hundreds, grouped in tens. 10 hundreds make 1,000. See?
Oh, I see. So that's 1,000?
Yes. And 10 of those
Exactly.
is great job. Yes. Let's do a real experiment right now.
Wow, what is it?
It's a surprise. Everyone, get ready. Good morning. Today we'll learn about experiments. Scientists test their ideas many times.
Many times.
Yes. Repeating tests make sure the results are reliable.
Sir, what do they find?
They find the output. Watch this diagram. The input goes through the process here.
Oh, I see. The output is the result.
Exactly. Great job. All right, class, let's solve these together. Who can help with 11 plus 3 plus 223?
237.
Excellent. Now 2 plus 28?
30.
Perfect. Great job, everyone. A coin toss is perfectly random.
Sir, so coin toss is not perfect?
It's perfectly random. Each side has an equal chance. So, like 50-50? Yes, only nearly fair.
But sir, is that fair?
Well, is it fair enough?
Yes, sir.
Then it's fair enough for us. Student, what affects fairness most?
Treating everyone the same, sir.
Excellent. Fairness is about equality. Okay, class, today we're learning about human flipping style.
Ooh.
It's a way to diagram human movements.
Like a backflip?
Exactly, you diagram the whole motion.
Wow.
Sir, can machines flip better?
That's an excellent question. Let's see. I'll flip this coin. And it lands perfectly.
Wow.
Yes, more consistent. The variables change, but the principle is consistent.
So, is the principle always the same?
Good question. The principle remains the same, but the variables change. All right, class, is perfect fairness possible?
Yes, if everyone gets the same.
But is same always fair?
No, some need more help.
Exactly. Fairness is about needs, not just equality. This concept is very difficult.
Very difficult?
I don't get it.
This is so hard.
Let's review the basics.
I have a question. Me too.
Sir, what is the main idea?
That's a great question. Who can tell me? It's the most important point. Exactly. Well done.
Oh, I see now.
Perfect. Let's continue. As you can see, real life is not perfect math.
What does that mean?
It means life is complex and unpredictable, not like these neat equations.
Oh, I get it now.
That's a great question. Who can tell me?
Is it for the test?
Partly. But more importantly, it builds your knowledge and skills for the future.
Oh, I get it.
Sir, where is this useful?
That's a great question. Math is everywhere, even in building bridges. These equations help us calculate the right materials and forces.
Oh, exactly.
Math is a powerful tool. In science games and decisions, we use the term SIR.
Sir, what's that?
Yeah, what is it? Cool. It stands for search, information, and result. It's how we make good choices.
Awesome.
All right, class, let's see how probability depends on conditions.
Like the weather?
Exactly. Let's roll some dice to see. A 5 or 6 would be rare. As you see on the board, a coin toss isn't always perfectly 50-50. Let's try it. I'll toss this coin.
It landed on heads.
That's a great example. So, is it always 50-50? Think about it. Always question simple assumptions in math and science. For example, the sun appears to move across the sky.
But the Earth is actually moving.
Exactly. Great job questioning questions. All right, class, let's talk about probability.
Like a coin toss?
It's a 50-50 chance. Exactly. That's the theoretical probability. But what about the experimental probability? We will continue the rest of the lesson tomorrow.
Yay!
I hope you're all excited to learn more.
Yes!
Great! See you all tomorrow!
Bye!